Hi, welcome. This is Clemens at Elektor. In the March-April 2020 edition of Elektor magazine, we published a remote-controlled switch with state feedback that communicated over LoRa. It was also housed in a IP66 waterproof enclosure, making it suitable for outdoor use. It was also a modular design with the relay and the power stuff on one board and the communication system on another board. Now this interested me because I was looking for an outdoor switch that I could integrate into my home automation system. My system is based on Home Assistant running Wi-Fi, but not LoRa. I'm sure you can use LoRa as well, but I didn't want to go into that. Instead, I thought I replace the LoRa module by a Wi-Fi module and make it run ESPHome that works great with Home Assistant. The schematic of the switchboard is not very complicated. At the top we have a power supply based on an AC/DC module Mod 1, which provides 5 volts together with some filtering circuitry. In the center is a bistable relay RE1, which switches the load on and off. A bistable relay is much like a mechanical switch in that it keeps its state even after its power is switched off, exactly like a light switch in your home. It has 2 control signals, set and reset, to toggle its state. These signals are driven by 2 MOSFETs, T1 and T2. Note that the relay is protected by a 5 amp fuse F2, even though the relay itself can switch up to 16 amps. The reason for this is that the PCB traces cannot handle that much current and the fuse protects them from melting. The switchboard can handle loads up to about 1 kilowatt. In the lower left corner we find the Opto Coupler IC1, which is in parallel with the load. When the load is switched on, the Opto Coupler is switched on too. Its LED will make its transistor conduct and the output goes low. When the load is off, the Opto Coupler is off and the output is high. C4 and R4 filter out a 50 or 60 Hz main signal, ensuring a nice steady level. The connector in the lower right corner makes all the signals available to the control board. S1 is intended for a push button mounted on the device, so the switch can also be controlled locally. A detail to be aware of is that the Opto Coupler is connected to a 3.3 volt supply, but there is no 3.3 volt supply on the board. This means that the control board also must supply a 3.3 volts for the Opto Coupler. We now know the specifications for the Wi-Fi control board. It needs 2 digital inputs, one for the Opto Coupler and one for the push button, and 2 digital outputs, one to control T1 and the other for T2. It must also provide 3.3 volts for the Opto Coupler output. Now, if you say 4 GPIO ports, Wi-Fi and 3.3 volts, then you immediately think of the ESP01 module, which has 4 GPIO ports, Wi-Fi and which runs from 3.3 volts. There is a but, however. The 4 GPIO pins of the ESP01 module must be handled with care as they determine the way the module works after power-up. GPIO 0, 1 and 2 must be held high at power-up. This is mentioned in the notes below the pin definitions table in the datasheet of the ESP8266EX. Most ESP8266 users know about the requirements for GPIO 0 and GPIO 2, but not everybody knows about the requirement for GPIO 1, which is also known as TXD, the serial port output. On the switchboard, the signals set and reset are always low at power up due to the resistors R7 and R8. The Opto Coupler output or on signal can be low too if the load happens to be powered when the module is switched on. This is possible because the relay is bistable and keeps its state even when it's powered down. Input S1 is floating and its state at power up is determined by the control board, unless it happens that someone presses the push button during power up. The signal is then low as well. So all in all we are dealing with 4 signals that can all be low at power up and that must be connected to 4 pins, of which 3 must be high at power up. Using an ESP01 module in this situation is therefore a challenge. The solution I came up with is as follows. A GPIO 3 or RXD is the only pin that can be freely connected, and so I connected it to the output of the Opto Coupler as its level at power up is unpredictable. RXD has to be configured as an input. When GPIO 0 is low at power up, the module will boot in flash programming mode. Now this can be useful if you want to reprogram the firmware, and so I connected S1 to GPIO 0. So GPIO 0 will have to be an input too. GPIO 1 or TXD and GPIO 2 are now left over, and so they will have to become outputs. To isolate them from the low impedances created by R7 and R8, I inserted P MOSFETs with pull-ups on their gates. This ensures that at power up, GPIO 1 and 2 will see a high level. When the ESP01 has finished booting, they can be reconfigured as active low outputs. The output driver now looks like this. When the GPIO signal goes low, the P MOSFET BSS84 will conduct. This will pull the gate of the N MOSFET BS170 high, and so it will conduct too, and the coil of the relay is powered. When the GPIO signal is high, the P MOSFET BSS84 will block. The N MOSFET BS170 will now also block due to the 1K pull-down resistor at its gate, and the relay coil is not powered. The 10K resistor ensures that the GPIO pin is pulled high at power up. For the 3.3 volt power supply, I simply added a low dropout regulator. In practice, R1, R6 and LED1 are not required, as they are already included on the ESP01 module. R5 is not needed either, but I added it just in case. With the inputs and outputs defined, we can write our ESPHome configuration YAML file. Now this is a bit more complicated than usual due to the bistable relay that needs 2 pins instead of 1. ESPHome and Home Assistant know a so-called covering component that can drive such peripherals, but it's intended for garage doors and window blinds and other peripherals that have a separate open and close button. They also have a special icon for it. Our switch is just a switch, and so we want it to behave like a switch and look like a switch. This can be achieved with a so-called template switch that lets you specify the behavior for the turning on and turning off actions separately. First we define GPIO1 or TXD as an inverted output named relay set. We also define GPIO2 as an inverted output and we name it relay reset. We also define GPIO3 as an active low binary sensor connected to the Opto Coupler. Then for the turn on action we specify a 100 millisecond pulse on the relay set output, and we do the same on the relay reset output as a turn off action. For the switch state we simply return the state of the Opto Coupler. To make push button S1 work as expected, meaning that pressing it will toggle the load on or off, we define GPIO0 as an active low binary sensor. If the load is active, then we switch the relay off, and if the load was inactive, then we switch the relay on. An if then else clause will do the trick here. After compiling ESPHome with this YAML file and flashing the ESP01 module with it, the Wi-Fi switch should pop up in Home Assistant and is then ready for automation. Okay, that's it for this video. Summarizing, in this video I showed you how to use the switchboard from the LoRa switch, but instead of using the LoRa communication module, we replaced it by a Wi-Fi module that we programmed with ESPHome to make the Wi-Fi switch accessible from Home Assistant. I hope you found it interesting and thank you for watching.